Okay, good morning, everyone. So last time we were talking about the free particle, but in a different way than we had before because we were talking about spherical wave solutions. So free particle, spherical wave, stationary states. That means eigenstates of the Hamiltonian. And this means that our complete set of commuting observables that we're using is going to be the Hamiltonian, the total angular momentum squared, and the z component of the angular momentum. Okay, and then there are kets that describe these stationary states, which we could write in a variety of ways. So one way would be like this. We're labeling by a number k, or we could just write it as the labels, KLM within the ket. Last time I think I used E, but it doesn't matter because there's a one-to-one correspondence between E and K. Okay, so the energy eigenvalue is equal to h bar squared k squared over twice the mass. So what that means is you can always interchange the energy label for the k label or vice versa. So can interchange E for k. And one thing I want to emphasize about these kets is one should not make the mistake of thinking of them as functions of position. So kets are not functions of r, theta, and phi. Instead, that's the wave functions that you get from the kets. So the wave functions, remember, are, we could write it like this, psi KLM without the angle brackets. These are defined to be the inner product of the position eigenkets r, theta, and phi, where the particle is known to have specific values of those coordinates. The inner product of that with the ket is the wave function, and that's what does depend on r, theta, and phi. Okay, and last time we worked out what these things should be, namely up to a normalization factor that we picked to be square root of 2k squared over pi. They are spherical Bessel functions of k times the radial coordinate times spherical harmonics, YLM of theta and phi. And I remind you, this is what we called last time the A-type solutions, which means that they're good at r equals 0. So if you're trying to describe something that's going on near the origin, these are the correct solutions. And for a while, we're going to be talking about solutions that are supposed to work everywhere. And so we will indeed want these A-type solutions. But just as a reminder, I'll put this in parentheses, or you could have same normalization factor times the spherical Neumann functions times the YLMs. And that's what you should use, or what you might want to use. These were what we called the B-type solutions that are bad at r equals 0, but might be good elsewhere. So later on, we'll talk about when you would want to use those B-type solutions. But for right now, if we're trying to describe a free particle moving throughout all of space, then we wouldn't want those. We would only want the A-type ones. Okay, and now some reminders of what these things satisfy. I'm going to write this in just a slightly different way than we did last time for variety. So first of all, there's orthonormality. And that says if I integrate over all positions with the correct normalization, r squared dr and d omega, of one of these wave functions with labels k prime, l prime, and m prime as a function of r, theta, and phi, multiplied by another wave function with a different values of KLM. Okay, that equals, I ran out of space there, but there's a delta function in k minus k prime, a Kronecker delta in L prime, and a Kronecker delta in M prime. So an interesting thing that's happened here is that we've got two different kinds of orthonormality within the same expression, because the k value is continuous. And so here we have a continuous thing, and so we use the Dirac delta function. And so we're using Dirac orthonormality. But the L and M labels are discrete because in fact they are integers. And so there we're using the ordinary orthonormality, and the whole thing has a product of those two kinds of orthonormality within it. And again, a reminder of the fact that it was a delta function in K rather than a delta function in E has to do with the fact that we chose our normalization here to make it be true. That's why we chose this particular normalization, is that so this would come out as a delta function in K rather than a delta function in energy, which we could have done. That would have been another valid choice. So that's the orthonormality condition. And then there was completeness, which you can write in a variety of ways. Okay, so one way you could write it is now, instead of integrating over all positions, I'm going to integrate over the K and L and M labels, or sum over them. Okay, and so we've got, because K is continuous, we're going to integrate over it. Oops. So we're integrating 0 to infinity dk. And we're summing over the discrete labels, all possible ones. Okay, and then we have psi of KLM, R prime, theta prime, phi prime, star, complex conjugate, psi KLM, R, theta, and phi. Okay, and then since I'm summing over all KLMs, that's a three-dimensional delta function of R minus R prime. And by the way, it looks like I forgot up here, that should have been complex conjugated. So there should have been a complex conjugate here. So that's one way of writing it. Another way of writing it is I do the same integral over all K, same sum over L, same sum over M, but now I do it with the kets. This is equally valid if that's equal to the identity operator. The preceding formula just comes when I put that into a R prime bra-ket pair, but otherwise it's the same expression. Okay, so we have all these nice things that these spherical wave stationary states satisfy. And the next thing I'd like to talk about is the relation between them and the momentum eigenstates, which are P, and they correspond to a different complete set of commuting observables, namely just the three components of the ordinary momentum, but these are also eigenstates of the Hamiltonian. And the reason they're eigenstates of the Hamiltonian is because the Hamiltonian commutes with the three components of momentum if it's a free particle because there's no potential. Okay, and so the eigenvalues, in fact, are the magnitude of P squared over twice the mass. All right, so what we're going to do to understand this relation is to use the previous completeness formula. So I'm going to start with the momentum wave function, or the wave function for this momentum eigenstate. But then I'm going to insert the completeness relation. Sum over all k, sum over all l's, sum over all m's. And I'm just inserting the complete set of states. In between the R bra and the P ket. Okay, so let's think about what this thing equals. First of all, on the left-hand side, we worked out a long time ago what that inner product is. It's the wave function for a momentum eigenstate, which is e to the I p dot r over h bar divided by 2 pi h bar to the 3/2 power. And on the right-hand side, let's look at this inner product, the last inner product here, and see what we can say about it. So one thing we know is the KLM and the P basis have one thing in common, and that is they're both eigenstates of the Hamiltonian. Okay, and so because they're both eigenstates of the Hamiltonian, they have the same eigenvalues. And so this will vanish unless they have the same energy eigenvalue, which is given by P. And so P has to equal h bar times k. So if it vanishes unless that's true, and P and k are continuous variables, that means it must have the form of a delta function in k minus magnitude of the momentum divided by h bar. So it's that times something. And what could the something be? Well, the something depends on L. It depends on M. We've already got the dependence on the magnitude of P, so the only other thing it can depend on is the angles of the vector P that appeared on the left-hand side. So let me just write down a completely general function of all of those quantities. I'm going to write it this way. I'm going to call it C because I'm thinking of it as a coefficient. So it's C for coefficient. It depends on L. It depends on M. It depends on the angle of the P vector in theta and the phi angle of the P vector. So it depends on the direction of P, but it doesn't depend on the magnitude because, again, the magnitude is already incorporated in the delta function. Okay, so it's so there we have it, and now there's a beautiful thing that's begging us to do something. We've got an integral over k, and we've got a delta function in k. And so the integral of a delta function is easy, and so let's go ahead and do that. It's begging us to do it. So here we write equals, and we're doing the k integral. Okay, so it's a sum over L, sum over M, okay, of R K L M, C L M, theta P, phi P. Okay, and so the idea now is to solve for those coefficients as unknowns. All right, any questions so far? Are we good? Okay, so solving for those unknowns is actually a bit tedious, and it's done in the notes, but I don't want to go through it in class because like I said, it's a little bit tedious. Let me just list the ingredients that go into the solution. So what we have here is we have some e to the I stuff. And on this side, we have a wave function for the KLM states, which we know. And we have these unknown coefficients. So the two things that go into it are, I'll just say here, uses, are two mathematical facts. One is e to the I k r cosine theta. And you can sort of see how that relates here. Cosine theta is what you get when you take the dot product of two objects. Okay, that turns out to be equal to a sum over L. There's no sum over M in this, but it's 2L plus 1, I to the nth power, that's the square root of negative 1I, times a spherical Bessel function times a Legendre polynomial. So that's kind of a magic formula. And then the second ingredient one needs is this. Let's say I have two unit vectors pointing in arbitrary directions. I'm going to call this one n hat and this one n hat prime. And I'm going to call the angle between them gamma. Then the nth Legendre polynomial of the cosine of that angle turns out to be 4 pi over 2L plus 1, sum over all m's of a given L times a product of spherical harmonics. And the two spherical harmonics that go here are the spherical harmonics for the two different unit vectors that appear in that expression. So there's some angles theta and phi associated with this first unit vector. That's what goes into this YLM. There's a different set of angles that go into that unit vector. That goes in this YLM. And then magically, if you multiply them together, and I see that I forgot again my complex conjugate, which is important because spherical harmonics are complex in general. But so magically, I multiply them together. Sum over all possible m's for a given L, which is fixed on the left side, with the appropriate weighting factor. Then I get this Legendre polynomial, which then you're matching up in that. That's the strategy of all this. So again, I'm skipping the details, so I'm saying put together. So what I'm about to say should not necessarily be obvious at all. Okay, but what you find is that your plane wave, e to the I k dot r, I could have written that as p over h bar, same thing. So this is equal to 4 pi, sum over all L's, sum over all M's, I to the nth power, YLM, and the angles that go here are the angles of the k vector. So I'm putting a subscript on the angles to tell you that those are the angles of the k vector. I'm not going to forget my complex conjugate this time. And then there's the spherical Bessel function and the YLM of the r vector. So for the r vector, for the position vector, that's the usual theta and phi that go in the end there. Okay, this is for r. These angles are for k. And so if you sum all this up, that's just equal to e to the I kr. So it's a very non-trivial expression because how do the spherical Bessel functions know anything that they're supposed to sum up to e to the I things? and they just sort of do. Okay, so that's our formula that does what? Let's say in words what we're doing here. On the left, we have a state of well-defined momentum. Okay. And the momentum is actually P equals h bar times the vector k. And what this equation says is that it's equal to, on the right, a superposition of all possible angular momenta. Okay, with the same energy. So with energy E equals h bar squared k squared over twice the mass, and same on the left-hand side. In both cases, that's the well-defined energy. Okay, but on the left-hand side, we're choosing to have it be an eigenstate of momenta, and then it's a sum over angular momentum on the right-hand side. And all this other junk, the I to the L, the spherical harmonic of the k vector, and the 4 pi are basically what you get when you solve for these unknown coefficients, what we call the CLMs. Okay, so that's the solution to that problem of writing one set of eigenstates in terms of another set of eigenstates. A long time ago, when we were talking about different CSCOs, we said that a lot of times in quantum mechanics, that's the central problem, is writing one set of orthobasis elements in terms of a different set of orthobasis elements. And so sometimes the problem calls for you to want to write things in terms of plane waves, but other times the problem will want you to write things in terms of angular momentum eigenstates. And so sometimes you have to be able to convert. And that's how you, this is what we just done is how you do it for a free particle. All right, so we can apply this technology to much more than the free particle though. And so I'm gonna do that now for the case of spherical well problems. Okay, and so we'll start with the simplest possible one, which is suppose that our potential, I'm going to write it as only a function of the radial coordinate to make it spherically symmetric. And it's going to be either 0 or infinity. So it's going to be 0 for r less than a, and it's going to be infinity for r greater than a. So if I graph it, of course, it looks just like this. There's r, there's a, okay, and it's 0. And then it bumps up to some very large value that we're calling infinity. Of course, there's no real infinity, but it has an idealization. It looks like that. Okay, and so what is this? This is a particle confined to a sphere or to a ball, as opposed to the one-dimensional problem that we did where a particle was confined to a box. Okay, so here v equals infinity. The particle is forbidden to be there. Okay, and inside the ball, for r less than a, the particle is obeying the same exact equations as a free particle. So that's good because since we know the free particle solution, we'll be able to write down the answer. So in fact, the wave function psi, and I'm labeling for variety, I'm writing it as energy rather than k, as a function of r, theta, and phi. we know is going to be some unknown coefficients times the solutions for a free particle, which we also know because they look like that. Okay, so notice that we have not included the Neumann function. We haven't because r equals 0 is part of our domain. And so we've only used the j's, not the Neumann functions. We'll use the Neumann functions for something later. And the other thing that's going on here is because we have to match the wave function at r equals a, this thing has to vanish at r equals a. So must vanish at r equals a, and that determines what are the allowed values of k. So not every k will be allowed, and that's going to give us the allowed energies. And once we know the allowed energies, then we can plug in and find out what are the allowed wave functions. Okay, so let's do it, and we'll do it with, first, we'll just consider the L equals 0 states, because they're the easiest. And so then if you look back at what the spherical Bessel function was for L equals 0, so J0 of k times r, that was very simple. It was just sine of kr over kr. Okay, so this, again, must vanish for r equals a, which tells us that the numerator has to vanish. And so k times a has to be equal to a multiple of pi for n equals some positive integer. So why is it a positive integer? If it was a negative integer, we would actually get back the same solution, because sine kr over kr, if I flip the sign of k, just gives me the same thing back because they're both odd functions. And k equals, or n equals 0 would give me 0 over 0, which is not well defined. So that's not a solution, not an independent solution either. Okay, so we know what the allowed values of k are, and we can just plug them into the energy eigenvalue equation. So the energy is equal to h bar squared k squared over twice the mass. We know that's true because it has to hold in this domain. And so if that's the allowed value of energy, it's the allowed value of energy everywhere. Okay, and so now we just plug in for k. This is h bar squared n times pi squared over 2 mu a squared. Okay, so those are the allowed L equals 0 and m equals 0 states. So there's an infinite number of them, and we can graph the wave functions. It's traditional to just graph the radial part of the wave function. And we're doing this as a function of r. And of course, the only part we care about is from 0 to a. Okay, and so sine kr over kr for the lowest value of k just does this, something like that. So this is the n equals 1 state. And then there's the, let me use a different color here. There's the n equals 2 state, which does something like this. And then there's the n equals 3 state. This was n equals 2. Oops. There's the n equals 3 state, which again, they all equal 1 at r equals 0. But this does something like that.
I'm sorry, Professor, what was the formula for the RR?
Well, oh, it's just equal to, up to a normalization factor, it's just equal to the spherical Bessel function.
Oh, so that's what you're drawing right now.
That's all I'm drawing is, yeah, this. I'm really drawing this right here. because there's an arbitrary normalization factor, but you can worry about that separately.
And you mentioned n equals 0 is not valid because it's not an independent solution?
N equals 0 isn't a solution at all, because then when I try to plug in n equals 0 here,
Oh, because of
then
the
k is going to be 0, and I have 0 over 0. It's just not even.
Okay.
It's not what, yeah. The negative ones are the ones that aren't independent, and they're not independent. They're okay solutions, but they're not different solutions, because if I plug in negative here, it's just going to give me back the exact same function as if k was positive. Okay? So those are the lowest few solutions, and we have this nice, neat formula for the energies. Maybe I should have put a subscript n on this to distinguish the different, oops, let's go back to black, the different possible energy eigenstates. Okay, and all of that was for L equals 0, and now we have to do it for every other possible value of L. Let's do L equals 1. Next. So now one has to look up the L equals 1 spherical vessel functions. So it's J1 of KR. And if you look it up, it turns out this is sine KR over KR quantity squared minus cosine KR over KR. These things get more complicated as L gets bigger. But again, this must vanish for R equals A. And remember that in general, K is equal to square root of 2 mass energy over h bar. So if we can figure out what the K's are, then we'll know what the energies are. Another thing is that because L equals 1, this energy level is going to be threefold degenerate, because there are 3 different values of m that you can write down. So this is a degeneracy equals 3, as opposed to degeneracy equals 1 for the ground state for these energy eigenstates. And so now we have to solve a more complicated equation here for what values of k will make this equal to 0 at R equals A. And so if you solve that, the solution is going to be tangent of k times A has to equal k times A. So we have to solve that equation for k in order to know what the allowed solutions are. So unfortunately, that can't be done algebraically, but we can do a graphical solution. And so the idea is we just graph this function, tangent Ka, and we graph the function Ka, which is easy, that's just a line, as a function of Ka, and wherever they intersect, that will be a solution. Okay, so I'm doing a graph as a function of Ka. And so on the right-hand side, I'm going to use blue for that. That's a straight line. And on the left-hand side, I want to graph tangent of Ka. Let me use red for that. And so the graph of tangent Ka looks something like that. This is where the tangent blows up is pi over 2. And then it goes through 0 at pi. And then it goes and blows up again at 3 pi over 2, etc. Okay, and so the lowest energy solution is going to be this point right here. This is the point where they intersect. This intersection doesn't count because that's at k equals 0, which we already said that's not an independent solution. So this is not a solution. Okay, and so This is the lowest energy solution. Just by making graphs of it, you can tell it exists, and then you have to tell your computer to find it for you. Okay, and then as we go on, there's going to be more solutions as we go off to the right, because we're going to keep graphing the tangent function, and it will keep intersecting that line. So the lowest energy solutions have k times a equals, it turns out, 1.430 something pi. And the next one is at 2.459 something something pi. Okay, and they keep going. So how would you do this in practice if you had a computer? One way you could do it that would be easy is you could define a function which is the sum, is the difference in the squares. So tangent squared Ka minus Ka squared. Okay, and that's a non-negative function, and it's 0 if and only if you have a solution. So you give that function to your computer, and then you give it an initial guess, which you might get from your graph. And you just say, okay, computer, sample all the points nearby that and keep minimizing until you get to 0. And then that's the solution, right? So that'll work. So that would be for a computer. And a lot of computer algebra systems will actually have these things built into them, where you can ask for a numerical solution to a transcendental equation like this, and it will think for a while and give you back these answers. But then once you have the k times a's, then you know the energies. So the lowest energy states are h bar squared over twice the mass times pi, I'm writing things in terms of pi squared over a squared, and then I just square these numbers, which gives you 2.046 for the first one, and 6.047 for the next one. And there's an infinite number of them, which you can generate. And so those are the energy eigenstates, or the energy eigenvalues for the L equals 1 solutions. Okay, and then there's L equals 2, where things are even more complicated. Because now what we have to write down is the L equals 2 spherical Bessel functions. I'm going to write these in terms of rho. Remember, rho was k times r. So this turned out to be 3 over rho cubed minus 1 over rho sine rho minus 3 cosine rho over rho squared. Rho is equal to k times r. Okay, and so now you need your computer to solve the equation second spherical Bessel function of k times a equals 0. So actually this can be done, it's not too hard to do it without a computer, because instead of the equation, going back up here, instead of this equation, tangent Ka equals Ka, it turns out this one gives you tangent Ka equals Ka multiplied or divided by 1 minus Ka squared over 3. So what does that mean? That means instead of here, when I did this blue line, instead of putting in a blue line, now I'm going to put in this curve, which is close to a line when Ka is very small, but then deviates for larger Ka. So in any case, I can just look for intersections of these functions. And it turns out that I've done this ahead of time, so I know the energy eigenvalues for L equals 2 are h bar squared pi squared over 2 mu a squared. The first one is 3.365, something, something, something. Of course, these are not exact. 8.381, something, something, something. And they go on forever. There's an infinite number of different intersections. Okay, and so now one can graph all these different energy levels as a function of the possible values of L. And so let's do that. So this is the energy in units of h bar squared pi squared over 2 mu a squared. Okay, and I'm going to separate out the different values of L, which are integers. And so first we have the L equals 0 solution. Let me put 1 here and 4 and 9 because those ones were exact. Remember, it was just n squared for those ones. Those were the easy ones. Then there's L equals 1, which has an energy level somewhere about here-ish, and another one up here somewhere. And then the next one is above up there somewhere. Then there's L equals 2, which had an energy level, what was it? It was 3.365, so it's about there-ish. And then 8.381, so it's about there. Okay, and then you can go to L equals 3, which has its lowest energy level there. And then there's another one somewhere up here. I don't remember where. I think there's a graph of these in the notes. But so these are all the allowed energy levels for a particle confined to a spherical ball, but otherwise free. Okay, so again, each one of these lines actually has degeneracy 3 for L equals 1. For L equals 2, I've drawn one line, but each line has degeneracy 5. And here, each line has degeneracy 2 times 3 plus 1 is 7, etc. A generic feature that's very common to all these problems is that the lowest of all the energy eigenstates has L equals 0. And then as you add angular momentum, the lowest available state, lowest available energy state gets more energetic. Classically, that's just like the fact that if I have something and I start rotating it, I'm adding to the kinetic energy of its parts. And so the energy has to increase. And so quantum mechanics knows the same thing. It's built into the equations that if I increase the angular momentum, the energy goes up. And so the lowest energy state is generically going to be an L equals 0 state with no degeneracy. But then the higher states do have degeneracy. This line should not be confused with that line. They're slightly different. So there's no accidental degeneracies between, for example, this one and that one. Why would there be? They're coming from solving some weird transcendental equation here. And so there are no extra degeneracies as there will be, it turns out, when we do more interesting problems like the harmonic oscillator in 3 dimensions and the hydrogen atom in 3 dimensions. Okay, questions on that? So let me discuss a slightly more general type of problem, and then you'll get to do one like this for homework. Actually, we'll do one more example of this, and then you'll get to do another one for homework. And that is to consider spherically symmetric potentials that are piecewise constant. So piecewise constant potentials. So rather than write an equation for them, let me just draw a picture of them. Here's potential as a function of distance from the origin. There's distance from the origin. And now my potential might look something like this. It's some positive value, goes to some negative value as a constant. Then it might go positive more, might go to 0, might go to infinity. Who knows? Something like that. But these different values are constants. Okay, and so in each range of R, it's obeying like a free particle. Because the Hamiltonian is the total momentum squared over twice the mass plus some constant v sub n. Okay, this I can call my free Hamiltonian. And so what does the eigenvalue equation for that look like? It looks like H0 times my ket has to equal E minus the constant potential part times my ket. And so E minus the potential just plays the role of the old E for the free particle. Otherwise, everything's going to be exactly the same. And so we know what the solutions are. Okay, so the wave function solutions are going to be these YLMs times spherical harmonics. It's just that we're going to replace h bar squared k squared over twice the mass, which used to be E. It's now going to be E minus V sub n in each region. And so in other words, k is going to equal square root of 2 mu E minus the constant value of V over h bar in each range of R. So the E is the same, but the K's are different in each range of R. I should write that down. E equals same, K different for different R ranges. Yeah, go ahead. Okay, so the solutions, therefore, are going to be for the radial part of the wave function, depend on the energy and the angular momentum. And there are going to be some coefficients. And there's A-type solutions. I'll label them by N for the different V's times JLKRs plus B-type coefficient solutions for the Neumann functions. So here's where the Neumann functions actually can play a role, because let's say I'm in this range right here. Now I don't have to worry about if something's blowing up at R equals 0 or not, because R equals 0 is not included in that range. And so I need to go ahead and include the possibility that I should include the B-type solutions in that range. So this is going to be true in each region. For that we're labeling N. N is 1, 2, 3, 4, 5, as I've drawn above. Okay, and so now to complete the problem, these unknown coefficients need to be solved for. And how are we going to solve for them? We're going to do one of two things. One is to match the radial wave functions and their first derivatives with respect to R at the join points. The join points are the places where the potential changes from one value to another. So that's a join point, that's a join point, that's a join point, that's a join point. Except that's true as long as the potential isn't infinite on either side. So if V is finite. And then at any point where V is infinite on either side, then you set the radial wave function to 0. So, or, it's a big or here, REL r equals 0 if v equals infinity at that r. Okay, and so the idea is by matching on either side of the join point what the radial wave function in the first derivative is, or by setting it to 0, you'll get enough equations to solve for these coefficients. And then once you've solved for the coefficients, then you'll know everything there is to know about the wave function. Okay, so we're out of time for today, but next time what I'll do is I'll tell you that there's certain complications that arise, which basically say that even though you can always choose to write things as a superposition of spherical Bessel and spherical Neumann functions, that's often not the most convenient thing to do. And so we'll talk about what's the most convenient way to deal with certain special problems. And then we'll do another example, which is the analog of the one-dimensional particle in a well, as opposed to in a box. And we'll solve that, and then you'll get to do another one, a similar, very similar thing for some future homework set. Okay, so by the way, homework set 9 is now available on the course webpage. The first problem, as promised, is from the midterm. And so hopefully that should be not too hard. And it's due a week from today. And then there will be 2 more homework assignments due this semester. All right, so that's it. Are there any questions about today's lecture? Okay, if not, then I will.
I'm sorry.
Go ahead.
Are there any resources where I can learn more about these functions, like these Bessel functions and these different functions that you're introducing?
Yeah, I mean, they're usually found in different texts on mathematical physics or just on math. One that's very popular is by Arfken and Weber. But there are lots of books on math and mathematical physics that go into great detail on spherical Bessel functions. So what I'm trying to give you in this class is sort of a need-to-know basis explanation of some of these things. So I'm not going to necessarily go through all the derivations, but just sort of explain to you the ideas behind them, and then give you some formulas that are necessary for working with them. So one example of that would be these things that I went over way back up here. So for example, these are 2 mathematical facts that you can prove, and it's actually kind of tedious to go ahead and prove them, but these are done in books like the Arfken and Weber book.
So would you recommend that, or is it not necessary?
I would probably say it's not necessary. It's sort of a standard reference that people will go to when they need to know more than what we will need to know. So it's a pretty thick book, pretty comprehensive book. And there's some other books. There's Matthews and Walker is another book that I think has a lot of explanation of some of these things. So,
what are the names of these books?
I don't know. I don't remember. But if you Google Arfken and Weber, then you'll find it. Or if you Google Matthews and Walker mathematical physics, you'll find it.
Thank you.
They're probably called, I think I have Arfken and Weber here. Arfken and Weber is called Mathematical Methods for Physicists. But yeah, if you Google Arfken and Weber, you're guaranteed to find it.
Okay. Thank you.
Okay, other questions? All right, and if not, I will see you virtually on Monday.
Thank you.